Hey guys, and welcome to a video about my favorite partial differential equation, Poisson's equation. Hi, my name is Frank and welcome on my channel. So, what is Poisson's equation? We start with omega being a domain, so omega is a non-empty open connected set. Then we are looking for a function y which satisfies the following conditions here. We are given a function u and we want the negative Laplace operator applied to y to be equal to this function u in our domain, and on the boundary we want our function y to be 0. So in one dimension, this Laplace operator here is just the second derivative of y. What are reasonable spaces for our functions y and u? Well, obviously a choice is to pick y in the space of twice differential function in the domain, and it should be continuous also on the boundary. And we want u to be continuous. If we have such a pair y and u which satisfies this condition and also satisfies our partial differential equation, then such a solution is called a classical solution. However, just look at the spaces here, they are super restrictive, and in fact in this video we want to show that the mapping which maps u to y can be understood as a mapping from L2 to L2, so it's just the quadratic, the back integrable function. This is just the base L2. This of course is a much nicer interpretation of this Laplace operator here, or of this Poisson's equation here, and this gives rise to many applications in optimization and, well, many more. To understand this video, it is helpful to have an understanding of analysis. In fact, we will use some multi-dimensional integration, differentiation, stuff like that. And also we will use basic results and tools from function analysis. So we will make use of the standard functional spaces like the LP spaces, and maybe you have heard of some Sobolev spaces, and we'll also use some common theorems. But any result which is not common and cannot be easily found with Google or with other internet search engines, I will post some remarks where to find this specific result. We start by building our toolbox. We first want to define the support of a function phi which goes from our space omega to the space R. We gather all the points in our domain where the function phi is non-negative, and we call this set support of phi. With this support, or with this definition, we can now define the so-called space of test functions. Therefore, we take all the functions phi which have a compact support and are infinitely continuously differentiable. This set is then called CC, or the space of test functions. In older books sometimes this is called Z0, but well, it's all the same. If you have done some function analysis, I'm pretty sure you have seen this space, because it's a very common space and it's a very useful space, and you will see later why it is called the space of test functions. An element from this test function space, of course, is called a test function. So we do some hand waving argumentation. Since if we have such a test function, this means the support is compact. This means the support is bounded and closed. On the other side, or on the other hand, omega is an open set. This means there's always some space between the support and the boundary of our domain. Or to put it in other words, if you have such a test function, then this test function can be continuously extended to 0 on the boundary. And this is a very useful property, and we will see this in analysis later on. We will make heavy use of this. So this is all I want to say to the space of test functions. The next element in our toolbox is the so-called weak derivative. We start in one dimension, hence omega is just the open interval from A to B, and u should be differentiable function from omega to R. The next step might a little bit look artificial, but you will see in a moment that this makes perfectly sense. So we start by taking a test function and multiply our function u with the derivative of phi and integrate over our domain omega. Since everything is smooth and differentiable, everything is fine, we can apply integration by parts and end up with the right hand side here. And you can see there is a term on the boundary. So u phi evaluated at b minus u phi evaluated at a. We now make use that phi is a test function and can be continuously extended to be 0 on the boundary, basically meaning phi of a is phi of b is 0, and this term here, this boundary term, drops out because it is 0, and we end up with this expression here. Let's take a closer look at this expression here. On the left hand side, we see that the derivative is in our test function phi, while on the right hand side our derivative is our function u. This makes perfectly sense as long as u is differentiable. But since our test function phi was arbitrarily chosen, this must hold for all of our test function phi. And this can be now used to define the so-called weak derivative, or to put this into a definition. We just replace this derivative of u with a function v and say, well, the function v is called a weak derivative if the following expression holds for all phi in our test function space. And we say that u prime, or derivative of u, is now called v. It is clear that every strong derivative is also, or a derivative, so a strong derivative is the classical derivative, that every strong derivative is also a weak derivative. But we will see in the examples later on that this definition here is weaker, in the sense that not every weak derivative is a strong derivative. So this is a useful definition, and in the next slide we will see where does the motivation come from. I mean, this was kind of a little bit, I just showed you and you say, yes, this makes sense, but this can also be motivated by the sense of distribution. We are now leaving the classical analysis and take a very short look at the theory of distributions, which had been defined by Lorenz Schwarz a couple of years ago. A distribution is just a linear functional defined on some test function spaces. And this is why the space CC is called the space of test functions. And we say for a given function u, the corresponding distribution is just a linear functional where you map a test function on the integral of phi times u and integrate it over the domain omega. And this is where the multiplication integration trick comes from. Keep in mind that not every distribution can be expressed as such a linear functional. For instance, the Dirac delta distribution cannot be showed in such a way. But if you have a function u, then you can make a distribution in the following sense here. So let's go back to our topic. Assume that u is differentiable and we call the derivative v. Then we can apply integration by parts. We just done it and we end up here. And here now comes the trick. Even if u is not differentiable, well, so the left hand side is not defined, we still can take the right hand side and define the functional here. And this makes perfectly sense in the sense of distribution. And in the theory, you see that things work fine if you call this functional is to call this function the derivative of u, in the sense of distributions, of course. So I hope this helps to understand a little bit where this test function and multiplication and integration comes from. This can be motivated if you use this, or if you know a little bit about distributions. Now it's time for some easy example. Let's take the one-dimensional function which maps x to norm of x. You have this V-shaped graph, and obviously the only point we are interested in is x equals 0, because there it's not differentiable. If you come from the left-hand side, the derivative is -1. If you come from the positive side, you have +1. But in x equals 0, it's not differentiable in a classical sense. In a weak sense, we have this expression here, or this function here, and you can see that this is in fact a weak derivative. This function here satisfies our definition. It's just an easy task, just plug it in, compute the integrals, and you see this works fine. And if you do this, you will notice that the value you put here at x equals 0 doesn't play a role. It's not important if there's a 0, if there's a 1. Just put in your favorite real number and you're happy. So we learn from this example that we in fact can compute weak derivatives of non-differentiable functions, and in general they are not unique. I will show you later that under certain conditions they are unique in the sense that you can vary them on a set of measure 0. Okay, so much for this easy example, and let's go a little bit to a non-intuitive example. We take the characteristic function of q. So I call this the characteristic function of q. It's the function is 1 if x is a rational number, or 0 if it's not. It's an interesting exercise, usually done in analysis, to show that this function is nowhere differentiable. But however, we can compute the weak derivative, and the only thing you have to do is you have to compute what is the integral over r over our characteristic function of q multiplied with the weak derivative, with the derivative of our test function phi. Well, it's obviously 0 because q has a measure 0 in the LP sense, right? It has measure 0, and therefore the characteristic function of q is 0 in the LP sense, and therefore it makes sense that it has the derivative 0, obviously, right? So much for two interesting examples. Let's move to higher dimensions, both in the degree of the derivative and into the spatial dimension. Let's start with the degree of the derivative. This is very easy. Just apply integration by parts several times, and you will get a second weak derivative or third weak derivative, whatever you want. It's more interesting to see what happens if you extend this definition to higher spatial dimensions. So let be omega a domain in the space Rn, and alpha a multi-index where we gather all the degree of the derivative. Then we say that v is the alpha weak derivative of our function u. Well, if the following expression holds, you can get this by integration by parts. And the most interesting part is the operator d. So d alpha, well, you can see the definition here is just the where we apply the derivation into the spatial directions. And the norm of alpha is just the sum of the alpha i's. So there's nothing really spectacular here. It's just a straightforward extension of this idea to higher dimensions. Let's collect some properties of the weak derivative. It is clear, well, by definition more or less, if a function has a strong derivative, so in the classical sense, it also has a weak derivative, obviously, and both coincide. Well, nothing spectacular here. More interesting is point number 2. Weak derivatives are unique in a sense that they can differ on a set of measure 0. And we have seen this in the example of the derivative of our norm. So we have this V-shaped property, and it doesn't play a role which value you put at x equals 0 because, well, this is a set of measure 0. So in the LP sense, who cares? So they are unique in this following sense. And most interesting is point number 3. We also can calculate, or we can prove that the rules, so the classical rules for the derivation of sums and products, well, they also apply for the weak derivative. You can check this by computing the definition of a weak derivative. And this is very nice because now this is a useful extension of the strong derivative, or a useful extension, let's put it that way. And we do not have to change some sum rules or some product rules or stuff like that. So In the following, we are now defining some spaces which make use of these weak derivatives because we will need them in our weak formulation of Poisson's equation. So this is our overall goal. So keep this in mind. We're still talking about Poisson's equation. We're just building up our toolbox to get there. If we gather all the LP functions which have a weak derivative of order alpha in one set, then you call this set a Sobolev space. And this is denoted with WKP, where K denotes the dimension of the derivative. And P denotes the order of the LP space. So this is a nice space, and in fact you can make this a Banach space with the following norm. You can see the norm here. So if P is less than infinity, you basically sum up all the derivatives and compute 1 over P. And if P is infinity, you just take the maximum out of it. But this resembles, of course, the definition of the P norm. And if you use this norm in this space, you'll get that WPK becomes a Banach space, so it becomes a completely normed space. This is now a fine thing. Completely normed space are usually a good thing. But we can go even a little bit further. For the special case, if you set K to be 2, then the space WK2 in fact becomes a Hilbert space with the following definition of a scalar product. And this is now super, because in function analysis you always want to have Hilbert spaces. And we denote this space WK2 with the definition of HK. So, and in our case, we are interested in the space H1, so we set K to be 1, and in one spatial dimension, we know that the norm becomes something like this. You see that we just add up the L2 norm of F plus the L2 norm of the weak derivative. It is quite enlightening to take a small look into history and to take a look at who was Sobolev and why are the spaces named after him. So Sobolev was a Russian mathematician, and his full name Sergei Sobolev, who was working mainly on partial differential equation and numeric mathematics. And quite interesting, in the beginning of the 1930s, he published 2 papers on so-called generalized functions. These papers had been known by Lawrence Schwartz. You know Lawrence Schwartz, the inventor of the distributions, or the so-called father of distributions. These papers are known by Schwartz. However, World War II started, and Sobolev was forced to work on the nuclear bomb program of the Russian Union. So he didn't have much time to continue his work. On the other side, Lawrence Schwartz had enough time to finish his work on distributions in France, so that's why it's called the father of distributions. But nevertheless, Sobolev has made some serious distributions to this work. And if you're working with partial differential equations, there's no way you cannot avoid the Sobolev spaces, because they form the very foundation of the solution theory of nearly every partial differential equation in a way or another. So they are a very important part of function analysis when it comes to partial differential equations. Let's continue our toolbox and take a closer look at the space H1 in one dimension, meaning omega is just an interval. Then you can prove that every function in H1 must be continuous. We have the inclusion H1 is a subset of the continuous functions. And this is interesting because this is only true in one dimension. In 2 dimensions, you can construct examples. You just fire up Google and search for examples. They are usually quite technical, but you can construct them, where you have a weak derivative and the function is discontinuous. But in 1 dimension, everything is easy. Not everything is easy, but everything is easier, let's put it that way, and H1 functions are continuous. And this is interesting because this allows us to continuously extend every H1 function on the boundary. The boundary here is just, in this case, -1 and 1, but we can continuously extend them. And this allows us to define the following important space, the space H01. Basically, these are all H1 functions with 0 boundary conditions. This is a quite useful space, and we use this later on. The question is now, okay, in 1D it's easy. We'll continuously extend them, define the space, everything is good. But what about higher dimensions? In higher dimensions, well, the functions are not continuously anymore, so we cannot just extend them. So what about this case? For higher spatial dimensions, we have to work a little bit more and go a little bit more into technical details. So here's the theorem we're going to need to establish our space H01. So omega is now a bounded domain, our space Rn, but with Lipschitz boundaries. So meaning that the boundary is basically smooth enough. Then we can prove that there exists a linear and continuous operator, which is called tau, which goes from the space H1 to the space L2, but on the boundary of our domain omega. And the operator tau does this in a specific way, meaning if we have a continuous function and not we have a continuous Sobolev function, which is also continuous on the boundary. So bar omega is omega plus the boundary. Then we know that the operator does basically nothing. It just maps the function to the value on the boundary itself. And this right-hand side is well defined, since we know that y is in z bar omega. And it does this almost everywhere on the boundary. This is a quite important result, because this is an operator. This operator can now be used to define the space H01. You can find it here. We just say, okay, take an element of H1 and say, well, the so-called trace operator, so tau is called the trace operator, applied to our function v must be 0. The existence of this operator tau is, of course, is highly non-trivial. And you can find the proof in the book of Freddy Drölsch, which is, well, the standard Bible book for optimal control of partial differential equations. Freddy Drölsch is a German mathematician. He studied mathematician in Freiberg, Germany, and is now working as a professor in Berlin, also in Germany. And he's kind of let's put it, he's the expert when it comes to optimal control of partial differential equation. And his famous book here was written in 1984. I was able to meet him on a conference a couple of years ago. And he's a quite interesting person. He's very smart and also very friendly, in fact. It was fun talking to him. Okay, that's enough for my story time. Let's come back to hard mathematician. That's why we're here. So this operator tau is just a technical tool to define the space H01, and you can find the definition here. And this is now independent of the spatial domain and independent of functions being continuous and stuff like that. Now it's time to combine some of these results. Remember the space of test functions? So the test functions was mainly the functions which are infinitely continuously differentiable with compact support. Well, they have a direct relation to our space H01. So again, let omega be a bounded Lipschitz domain. Lipschitz domain, we need to define our space H01 using the trace operator. Then we can show that the space H01 can be interpreted as the closure of our test function spaces with respect to the H1 norm. And this is a very interesting result, because this allows us to approximate every function of H01 as a sequence of test functions. And this is a very strong result, and we'll use this later on. So here you can see it here. For every function in H01, we can construct now a sequence of test functions such that we have a convergence in H1. And furthermore, we will use this later, that convergence in H1 also implies convergence in the space L2. Well, you can see the estimate here. It's very, very easy. Just take the L2 norm of what we want to show, which should go to 0. And this is, of course, less or equal than the H1 norm, and the H1 norm goes to 0. So this proves our point. This is just a small remark. But the result here is non-trivial, of course. and you can find a result in the book of Martin Dobrowolski, Applied Function Analysis. By the way, Martin Dobrowolski was or is a German mathematician who was lately working in Würzburg as a professor, but now he's retired. He was mainly working on partial differential equations in the context of fluid dynamics. So Euler equation and stuff like that. I also met Martin Dobrowolski a couple of years ago, so that's why I put this reference here. But you can also find this result in every book about Sobolev spaces or partial differential equations, of course. Oof. Okay, we're now a couple of minutes into this video and we have learned a lot of technical stuff. We have learned about H01, Sobolev functions, test functions, distributions, and many more. But what do we actually want? We want to solve a Poisson's equation. You can see it here. So how is the knowledge of H01 helpful here? Well, we're close, but we're not already there. We have to add some more things to our toolbox, namely Gauss theorem. I'm pretty sure you've heard of this before. We need omega to be a bounded, open and bounded domain, and the boundary should be smooth enough. Then we can show that for every differentiable vector field, the integral over the divergence can be expressed as an integral over the boundary. This is a strong result. It's a quite deep result actually, and you have to do a little bit of analysis to prove this. But once you have it, you can use it to prove the next theorem, which I call integration by parts. Let's take a look at this. We have omega is again a bounded open domain with smooth boundary, obviously because we want to use Gauss theorem to solve it, to prove it. And f and g now should be twice differentiable functions from omega to r. So the difference here is in Gauss theorem, f had to be a differentiable vector field, while by integration by parts, f and g only have to be normal functions, right? So what's the point about this theorem? Well, let's take a look at it. Here we have the second derivative of g, while in all the other expressions we only have the first order derivative of g. And this is similar to integration by parts, where we shifted the derivative from one function to another. And this is the same thing happens here, right? We have second derivative on g. Here we have the first order derivative on g. Here we have no derivative on f, while here we have a derivative of f. And we pay a price. We have some integral over the boundary left. So this is the same thing as the normal integration by parts. The proof is quite simple. Of course, we use Gauss theorem of a suitable chosen function f. And for this function f, you just choose f of x times gradient of g. This is now a vector field, hence we can apply Gauss theorem. And well, there you go, just plug in everything and you are done. So nothing spectacular here, just plot it in for convenience. We now have all the tools available to actually move to a weaker formulation of our Poisson's equation, and we do this by using integration by parts. Let's start with a smooth solution of Poisson's equation. It should be smooth enough so that we can use integration by parts, of course. We now use the same trick as in the construction of the weak derivative. We multiply our Poisson's equation with a test function and integrate over the whole domain. So here you can see the Poisson's equation multiplied with our test function phi and integrated over the whole domain. And now we are applying integration by parts to the left part of this expression here. And you can see this result, you see the result here. And again, the trick is now, here on the left-hand side, we have second derivatives, while on the right-hand side, we only have first-order derivatives, especially applied, if you look at y. And this is nice because we have reduced the order of the derivative. Now we make use that phi is a test function to kind of get rid of this boundary term here. So a test function means it is a zero on the boundary. It's the same trick as we have used in the weak derivative. So this term here is essentially 0, since phi is 0 on the boundary, and the integration by parts, or this expression here, reduces to this term here. So the fine thing is here no boundary term, and the second derivatives on y are reduced to first order derivatives of y. This is now very nice, because what do we have achieved now, right? We started with Laplace equation and ended up with an integral formulation, but we get a reduction of the derivatives. So here I've written it again, integration by parts enabled us to get rid of the second derivative. Since our test function phi was arbitrarily chosen, this integral expression must hold true for all phi, right? And this now enables us to define a possible weaker solution of Poisson's equation. It is clear that if we have a smooth solution which satisfies this expression here, this Poisson's equation in its strong form, it also has to satisfy this integral equation here for all test function phi. It's the same idea or the same trick as in the definition of the weak derivative. We now use this weaker formulation here as a possible definition for a weak solution of Poisson's equation. I've written it down here. We only need in this case that our right hand side is in L2. Then we call a function of h01 a weak solution of Poisson's equation if the integral expression we just derived hold for all test functions phi. So this looks like a good definition, but if you now move a little bit further, because we want to show existence, this is just a definition, this doesn't state anything about uniqueness or existence at all. If you want to do some analysis, you run into some problems. Where are the problems located? Well, in the end, we want to use the very famous Lax-Milgram theorem to prove existence. But here we have different function spaces. We have h01 for our function y, and the test function space cc infinity for our test functions phi. And there, well, one is the closure of another, of course, and this is now the idea to continue. But first of all, they are different, and this makes problems in the Lax-Milgram theorem. I want to point out that there is a weaker formulation of the Lax-Milgram theorem where the spaces used can be different, but here cc infinity is not even a complete space with respect to the h1 norm. So this does not work here. So let's try to get rid of this cc infinity space. And to do this, we have to recall some results from analysis. First of all, we know that cc infinity is dense in h01, or put in other words, the closure of cc infinity with respect to the h1 norm is the space h01. Number two, convergence in h2, of course, implies convergence in L2. This is trivial, and we showed this before. And we need another result from analysis. If we have a converging sequence in L2, so fn should be some L2 functions and they're converging to an L2 function, then we know that we can move the limits into the integral. So let's combine everything. We take an arbitrarily chosen function phi of h01, then we know that there is a sequence of test functions converging to this function phi in the space h01, and using point number 2 and point number 3 we can move the integral the limits into the integral. How is this now helpful? Well, let's assume that the following integral expression holds true for all test functions phi, and let h in h01 be arbitrarily. Then we know that we can find a sequence of test functions which are converging in our space h01. Since phi n are test functions, this integral expression here must hold true. You can see this here. Now let's plug some limits in front of it, and now let's just move the limits into the integral, which we are allowed to. And we know that phi n is converging to h. So we know that the integral expression we started with also hold for our arbitrarily chosen function h on h01. Since h was chosen arbitrarily, this expression here must also hold true for all h in h01. And this is now finally our definition here. This is now the definition of the weak solution of Poisson's equation. Again, u should be an L2 function. Then we call y in h01 a weak solution of this expression here. If the integral expression here hold true for all functions in h01. This is the only difference to our definition before. In our definition before, we had here the test function space, but you can replace it by the space h01. And this is now perfect because this enables us now to apply Lax-Milgram to get existence and many more results. As you can expect, of course, we do have uniqueness and we do have existence, and this is gathered in the next theorem. We have chosen the correct spaces, we have chosen the correct definitions, so that we can now show that for every u in L2, the Poisson equation has a unique weak solution in the space h01. This can easily be proven by the Lax-Milgram theorem. You can find the proof, for instance, in the book of Troeltsch. And even more, we do not have only existence and uniqueness, we also have some stability, meaning that the solution y is bounded in the h01 norm by the L2 norm of u. And this is sometimes helpful when you want to prove some error estimates or something like this. Oof. Okay, we are finally there. We now can identify a mapping. So here you can see the result again without the stability estimate. But we can now, for every u, we have a unique y. So this, of course, defines a mapping from, which I want to call S, from L2 to the space H01. But the space H01 is, of course, a subspace of L2. And this is now finally our final mapping. We are done. We made it, guys. We made it. I have shown you how to interpret it, how to interpret the Poisson equation as a mapping from the space L2 to L2. I hope you're still with me and I haven't lost too many people on the way. I know it's quite technical in contrast to the videos I do usually, but I think this is a very interesting topic and you can learn a lot just looking at this very simple Poisson equation. I mean, it's a prototypical, simplest equation you can come up with, but you can learn so many things. I mean, imagine we started with the weak definition or with the weak derivative, extended this to higher dimensions, learned about Sobolev spaces, learned about a little bit about distributions. We then moved on using deep analysis results to integration by parts and adapted the idea of the weak derivative to our Poisson equation. And wow, this was a long way. But I think this is very interesting. I was working in the optimal control of partial differential equations, and this is my world. You know, I love working with the partial differential equations, especially when it comes to optimization. This is super interesting. You can dug into function analysis, and this is super interesting. But for now, I want to just mention that sometimes even a weak solution is too strong, because if you take a look, you have u in L2, and this sometimes is too restrictive. So I want to finish this video with an outlook to the so-called very weak solutions. The idea is very simple. You integrate by parts twice. And then you move the second derivatives on our function y to our test function phi. Of course, this comes with some higher restrictions. For instance, we have to choose different test function space and other restrictions. I don't want to go into details, but I also want to mention that we now have u basically in L1, So we reduce from L2 to L1. Sometimes this is even too strong, because when it comes to when you're doing optimization of partial differential equations, and your constraint is a partial differential equation. When you want to apply a Lagrange approach, you have some Lagrange multiplier for your constraint. But what if your constraint is a PDE? This is a priori not clear, but you can deal with some complex, or actually not so complex, but with let's put it with fancy function analysis, and you end up with your Lagrange multiplier being a measure. So not even a function, being a measure, for instance, a Borel measure. And now U is a Borel measure. And then you have to think about, okay, what happens if your PDE, the right hand side of your PDE has a measure? And things get crazy. And I think I stop here now before I start talking in a couple of hours. I hope you enjoyed this video. Thanks for watching. Thanks for staying with me throughout this technical video. And if you have any questions, just feel free to write me an email or write a comment here on YouTube. And again, thank you, and enjoy. Have a beautiful day, and see you in the next video. Bye.